Chapter 2, Atoms, Ions, and Molecules, Part 1. So this is now the chemistry part of the course. We'll be talking about atoms and molecules and moving up even into macromolecules in Chapter 2. So, surprise, surprise, the human body is composed of matter. And there are three forms found in the human body. You have solid, which comes as an example of bone, liquid, for example, blood, and gas, such as the oxygen that's brought into our lungs and is dissolved in the blood. So I'm sure you know, with water, ice is solid, water is liquid, and steam is gas. So that's just sort of another way to think about those states of matter. Matter is composed of atoms. So atoms are the absolute smallest that a particle can be and still have all the expected chemical properties. So an atom is the smallest particle possible for any element. Oh wait, what's an element? Well, there are a lot of elements. Looks like 118 or so. Elements are just the different kinds of atoms. We have hydrogen, helium, lithium, beryllium, and so on. Lucky for us, the human body is mostly made up of the different elements that you see in the extended blocks, hydrogen, carbon, oxygen, so on. So these are going to be the main elements that we will be concerned with this semester. So make sure you know the symbol. So if you see a C little a, you'll know that is calcium. If you see an Mg, that's magnesium. So when we talk about atoms, we know that atoms are made up of three subatomic particles. There are the neutrons found in the nucleus. The neutrons are neutrally charged, have no actual charge. Then we have the protons also found in the nucleus. The protons are positively charged. Neutrons and protons are around the same size, around the same mass, and they are found exclusively in the nucleus. And then spinning around the outside is the electrons. Electrons are negatively charged subatomic particles, and they are extremely tiny. So if you imagined a human being weighing, say, I don't know, 180 pounds being a proton, then an electron would be a mosquito flying around that human being. So electrons are extremely tiny compared to protons and neutrons. It's also worth pointing that this little shell model image we see is somewhat inaccurate, doesn't show the relative sizes correctly, doesn't show the relative distances correctly. If that mosquito is the correct distance that electron would be flying around that human proton, then the mosquito would have to be in, say, San Francisco while the person is standing in Los Angeles. So huge distances between the electrons and the nucleus. And also, instead of rings, it actually is more of a shell. So the electrons form a shell surrounding the nucleus three-dimensionally. All right, so when we look at the periodic table, we see an elemental symbol. Here is hydrogen. Above it is a number. That is the atomic number. Atomic number means the number of protons. So hydrogen has one proton. And then below that is the atomic mass average. So on the periodic table, we get the atomic mass average, in this case 1.008. So basically they take the average atomic masses of all hydrogens that we know of and average it. So most hydrogen atoms have just one proton, but there are some that are out there that are bigger than that. So atomic mass number of protons plus the number of neutrons. So for the standard hydrogen, it would be one proton, no neutron. So atomic mass and atomic number would be the same number. Now, we have already shown you the periodic table. So within the periodic table, all of the elements are organized based on the number of protons. So hydrogen 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, and so on as you go along the periodic table. So here is a cartoon of a carbon atom. So we can see that the carbon atom has 1, 2, 3, 4, 5, 6 neutrons and 1, 2, 3, 4, 5, 6 protons. So in this nucleus, there's a total of 12 subatomic particles, giving us the atomic mass number of 12. Since there's only 6 protons, that means it has an atomic number of 6. And when we also look at this, we see 1, 2, 3, 4, 5, 6 electrons. So the number of electrons in a uncharged or neutral atom equals the number of protons. So anytime we're saying atom in general, you're going to assume the number of electrons equals the number of protons and that the atom has no inherent charge. So the electrons are not all in just one space surrounding the nucleus. It turns out they are in different shells or orbitals. So on the first level energy shell, you can have a maximum of 2 electrons. On the second energy shell, on the second electron shell, you can have a maximum of 8 electrons, third shell maximum of 8, fourth shell maximum of 8, and so on. So that is what we're going to go by for this course. No, it can get more complicated, and they talk about that in chemistry course. But for us, first electron shell, 2 electrons, other shells, 8 electron max. Again, the shells closest to the nucleus are the ones that get filled first. So the first electron shell will get filled with 2, and then a third electron will go out to the second shell, and so on. And the outermost electron shell for any atom is called a valence shell. And it is the valence shell and the number of electrons in the valence shell that determine the chemical properties of that element, which means that various elements that have similar number of electrons in their outermost shell have similar chemical properties. When we look at the periodic table again, we know, of course, the order is based on number of protons or atomic number. They also organize the elements based on the number of shells and the number of electrons in the outermost shell. So each row is how many electron shells that element has. So hydrogen has 1 electron shell because it's in the first row. Lithium has 2 electron shells because it's in the second row. Sodium 3, potassium 4, and so on. And then we also see that the number of electrons in the outermost shell, so the number of electrons in the valence shell, can be determined based on the column that the element is in. So lithium is in the first column. It has 1 electron in its outermost shell. Beryllium in the second column, so it has 2 electrons in the outermost shell. Boron in the third column. Boron in the third column, that means it has 3 electrons in its outermost shell. Carbon is in the fourth column, so it has 4 in the outermost electron shell, and so on. The only slight exception to this rule is helium only has 2 electrons in its outermost shell, and it's in the 8th column, while all the others below it have 8 electrons in their outermost shell, neon, argon, etc. So if I had a question on an exam and I was like, how many electrons in the outermost shell for calcium, you'd know because you get a chance to look at a periodic table and go, oh, look, it's in the second column, so it must have 2 electrons in its outermost shell. So for an example, oxygen. Oxygen over here has 8 protons, so its atomic number is 8. It has 2 shells, 2 electron shells, because it's in the second row. And it has 6 electrons in its outermost shell because it's in the 1, 2, 3, 4, 5, 6th column. I know we're skipping about talking about these in the middle here. We're not going to go into those in any great detail in this course. Potassium, way over here. 19 is the number of protons. That's its atomic number. It has 4 energy shells, 1, 2, 3, 4 in the fourth row, and it has 1 electron in the outermost shell because it's in the first column. Isotopes. Isotopes are the same element, but different atoms in that element. And what makes the isotopes different is the number of neutrons. So same number of protons, same number of electrons, different number of neutrons. And so basically it is identical chemically to the other types of isotopes for that element. So carbon, there are 3 isotopes, carbon 12, carbon 13, carbon 14, each with a different number of neutrons. And of course, the average atomic mass is determined by averaging the occurrences of these isotopes in nature. Some isotopes are radioactive and unstable, so they're referred to as radioisotopes. They end up losing some nuclear components as they break down, and those lost components of the nucleus are what cause the radiation. So alpha decay, the nucleus of that element is going to lose a alpha particle, which is actually 2 protons and 2 neutrons. Very large particle, so it can be blocked by paper. So here's plutonium becoming uranium by losing 2 neutrons and 2 protons, an alpha particle. For beta particles, what happens is the nucleus loses an electron, loses a negative charge, so it is turning a neutron into a proton. So a positive charge gets left behind when the negative charge, the electron, leaves. So carbon-14 loses an electron from its nucleus, a beta particle turns into nitrogen-14. Beta particles are pretty small, but they can be blocked by aluminum. And then finally, we have gamma quantum radiation, gamma quantum that are released. Here, the nucleus is losing energy, so it's a photon. It's energy that's being lost. There's no change in numbers of protons, so it is still the same element. It's just more stable now that it's gotten rid of that excess energy. And it turns out that gamma quantum are able to pass through paper, aluminum, and needs to be blocked by a thick layer of lead. So very, very dangerous. The half-life for radioisotopes varies from one to another. The half-life is how long it takes for half of that radioisotope to decay. So for instance, we have carbon-14. It takes 5,730 years. Phosphorus 34 takes 14.26 days and can be used in leukemia therapy. Iodine 123 takes 13.27 hours, often used in thyroid therapy. So we use these radioisotopes for various studies and medical treatments. So for example, with the thyroid, all of the iodine that we consume ends up in the thyroid gland. So if someone has hyperthyroidism, they can take a radioactive iodine in order to damage the thyroid so that it produces less hormone. Also, if they think maybe there is a tumor in the thyroid gland and they want to determine if it's a passive benign tumor or a active cancerous tumor, then they can also supply the body with the radioactive iodine and then see how it's distributed in the thyroid gland. And if it's a benign nodule or benign tumor rather than a cancerous one, then you wouldn't see that much radioactive iodine showing up where that nodule is. And since it has such a fast half-life, the person doesn't have to go in any sort of isolation or anything. All right, that is it for this part of Chapter 2.